In this video, I am going to explain algebraic de Rham cohomology in a checklist fashion. So, algebraic de Rham cohomology. So this will be basically from chapters 3 and 5 of my book. So we start with the projective variety. We assume that it is a smooth projective variety of dimension equal to n. It's over a field K and characteristic K equal to 0. So what we want to define is this notation, the Rham xk, which we call it algebraic Rham cohomology. For this one defines something called hypercohomology that I will explain it in our example. And it is the hypercohomology of the complex of differential forms, algebraic differential forms over X. So as said, we have that this complex of differential form, differential operator here, it goes until omega n. When you reach omega n plus 1, it is already 0 because there is no n plus 1, n plus 2 differential form, algebraic differential form over X. And for this, it also will take a covering U with UI, I and I with Zariski open sets. And it will turn out that at the end, all these intersection UI0, UI1, UIGs are affine. And so Zariski open set, Zariski actually affine varieties. Anyway, so what I will need to define this SIG. What is this SIG? This is the subset of the product over all ordered set of G plus 1 element, let's say UI0, UIG plus 1 of the covering U. So this will be differential I forms in this intersection of G plus 1 affine variety. And this subset is characterized by skew symmetry property. What is this? This means that omega of permutation of, let's say, I0, Ij. So this permutation will not affect this intersection. So this will be -1 sine of the permutation, the same omega I0, omega I1, omega Ij. And by the way, I have to say that I have taken element omega I0, I1 until Ij. The element of this guy will be denoted by this one. So this product means that I have a bunch of these elements. It turns out we have a double complex of SIG. So there will be a map from SIG from left to right, Si plus 1 J. This is differential form, and there is also this check cohomology differential operator map, SIG plus 1. So this delta is the differential map in check cohomology. It goes from SIG to SIG plus 1, and its definition is this one. So it is in the intersection of G plus 2 open set it is just defined as k equal to 0 from 0 to g plus 1. We just make this sum minus 1 over k fi0, then fik, we just remove fik, and then fij plus 1. And this is the definition of the delta. And here I have to mention that at the end there is a restriction of this guy to this G plus, the intersection of G plus 2 open sets. Anyway, we get this double complex, and when we have a double complex, we get a usual complex in this set. So L0 will be just this one. L1, if this will be sum of these two guys, this one and this one. L2, the sum of these three guys. And in general, Lm upper script Lm will be sum of Si, Si, J, L plus J equal to M. And we have a differential operator D going from Lm to Lm plus 1, and the D on Sig is given by delta plus minus 1 to the G D. And so this G is the index of the corresponding to check cohomology. And it turns out that this have D composition with D is equal to 0. As once we have this situation, we can define the corresponding cohomology. So we define this cohomology, which is kernel of Lm going to Lm plus 1, this D over the image of map, the same map D from Lm minus 1 to Lm. This fulfill will be the hypercohomology of X of the complex of differential form over K, and the hypercohomology is a more general concept, and in our context this is just the algebraic de Rham cohomology that we are talking about. Okay, so now we want to discuss the fact that this algebraic de Rham cohomology is the same as usual cohomology when we are working over complex number. And before this one, we have to verify that this is independent of the covering U. In the book, you can find all the details of this fact, but for our purpose, we can just ignore this dependency on U. Okay, so whenever we are our complex numbers, we have the C infinity manifold. Sometimes we put it upper script infinity, saying that this is also C infinity manifold. And if we look in this way, the complex of algebraic differential forms is inside the complex of C infinite differential forms. In this way, this inclusion will give me a map from the algebraic de Rham cohomology to the hypercohomology of the same X, sometimes I do not write this upper script infinity, of the complex of C infinity forms. And this hypercohomology, it is actually isomorphic to the classical de Rham cohomology. So the classical de Rham cohomology, I will just use HM de Rham X algebraic with /RC. So this isomorphism in the book, it is proposition 3.2, but I don't want to make this this separately. Actually, what I want to explain that since we are going to, this is also an isomorphism, so we have this canonical map from A to here, and its inverse from uh, algebraic de Rham cohomology to visual cohomology. And I would like to make the description of these two maps. First, I would like to describe the map R-1 from the algebraic de Rham cohomology to usual de Rham cohomology. So I will take a representative of an element here. So what is this representative? It's a collection of zero forms, one form, and so on. Remember the structure of my double complex, so I am writing similar uh, to the double complex case. So this is my differential form. So its d is equal to 0. And in particular, the delta here is 0. So delta of omega 0 is 0. But something that we'll learn in topology, that the sheaf of differential, infinity differential form over x, it is 0 for all m bigger than or equal to 1 and k equal to 0. So these sheaves, C infinity forms, they do not have non-trivial check cohomology. So once delta is equal to 0, then this means that there will be some eta 0 C infinity form such that by delta it maps to omega 0. Now the trick is this one. Replace omega with omega minus d eta 0. In the forthcoming discussions, I will ignore some sign problem. It might be minus or plus. One has to uh, write down explicitly. But when you do this one, I will have still the same representative in hypercohomology, but omega 0 will turn out to be 0. So this means that I can assume that omega 0 is 0. And in the same way, then we will apply omega in the next step. Omega 1 will go to 0. Again, it will come from some another eta 1. I will modify my element of hypercohomology with differential of this eta 1. I can assume that omega 1 equal to 0. And at the end of the day, after repeating this procedure many times and using that these cohomologies are 0, I can assume that omega is just omega m. This means that there are no other pieces. And so we have the omega m equal to 0. Omega m is alone. So its delta goes to 0. Its d goes to 0. This means that delta omega m is 0 and d omega m equal to 0. So what it means, delta omega m equal to 0, this means that the pieces omega m is actually a collection of m forms defined over ui. So this collection of m forms, they glue to each other, they give a global differential form, and this global differential form is closed. And so we will, at the end, we will get an element in the classical de Rham cohomology. Now I want to make the description of the map A from classical de Rham cohomology to algebraic de Rham cohomology. So we have to take a global closed M form and we have to the get element here. In my discussion, whenever I put check on some notation, this means that's infinity. When I don't put check on some notation like omega, eta, this means that these are algebraic. Hopefully, this will make the understanding smoother. Okay, so let's go. We have this LM, okay? And so first consider Lm corresponding to C infinity, the complex of C infinity differential form. I started from my omega check. So I will get an element in Lm. How? omega m check, and omega m check, what it is just a collection of omega check restricted to ui and I, the index of my covering. So this will be its t is equal to 0 because my omega check is exact, and its delta is equal to 0 because this omega m comes from a global differential form. So at the end of the day, this is an authentic element. In this we have d omega m check equal to 0. So from this one, we want to get some algebraic differential form here. So let's assume that we have find a representative, let's say omega m minus 1 until omega k plus 1, it is algebraic, but in omega k it stops, it's not algebraic, that's why I have put 0 here, and the rest are 0. So the idea is that I want to make this omega k algebraic by adding something to infinity here and so on. So let's start. So we know that this d and delta, d of this one is delta of this one up to sine. So what it means, delta of omega plus 1 is equal up to sine, it is d omega check k. What this means? This means that this element is exact, but this element is algebraic. And uh, in one of the lectures, we will learn about a theorem called Atiyah-Hodge. And one part of the theorem says that if an algebraic differential form is exact in C infinity context, it is also exact in the algebraic context. What this means that I can find algebraic form omega k such that at the end of the day omega k goes with the differential to the same object here. And this means that if I make the difference of omega k with omega k check, it must go by differential to 0. Now, once again, we use Atiyah-Hodge theorem. We have exact differential form. We have, closed differential form on an affine set. So here, the affine set, the intersection is the intersection of m minus k plus 1 open set. This is a closed differential form. And again, Atiyah-Hodge theorem, the second part, says that this differential form is represented by an algebraic differential form. So so this means that there will be another algebraic differential omega till k, such that this and this, they represent the same element in the Rham cohomology of the affine set. So we just make this replace omega k with omega k minus omega till k, and we can assume that this guy is at the end of the day, it is 0. This means that it comes from the by d come from some omega k minus 1. So we are almost done. So we twice used the Atiyah-Hodge theorem, actually two different parts of the Atiyah-Hodge theorem to get this picture. So now we modify omega with the minus. This means that I will add plus minus 1 of this guy uh, uh, to my element. So I had omega equal to omega m plus omega k plus 1 plus omega k check. So once I, so here there is a k. Once I do this one, this will be cancelled. Here I will get purely algebraic element, but of course I am doing delta on the other side, so this will turn out to be omega m plus omega baba omega k plus 1 plus omega k. This algebraic, but there will be some non-algebraic thing here coming here, which will be exactly this delta eta k minus 1. So the basic idea is that we can continue this process, and this process reaches uh, until the end, and there we can get a purely algebraic element here, and so we construct the map A. So why we need this map explicitly? The reason is that we have a lot of topological constructions like wedge product in the classical de Rham cohomology, and also the concept of integration, delta being in HM x z. And since this map A is unique, then we can translate these things here. So here, the wedge product will turn out to be a cup product. And what it means that we can also define the concept of integration with elements here, but what it will be just integration of I minus 1 omega over delta. So the moral of the story is that we can integrate the elements of the algebraic de Rham cohomology over topological cycles.